Hi everybody, and welcome back to my lecture series on hardware for deep learning. I'm Dr. Adam Teman of the EnICS labs at Bar-Ilan University. Today we'll be going over part 5, which I called the Deep Learning Acceleration Landscape. So there are 5 parts to today's lecture. I'll shortly overview parallelism in deep learning, then I'll go to traditional programmable hardware, specialized deep learning hardware platforms, the deep learning software stack, and finally some specialized research ASICs. So let's start with parallelism in deep learning. So I just want to show a categorization that's common to find about this embarrassingly parallel problem of deep learning. So one way of parallelism is what we call data parallelism, where say we have 4 different machines here and we give the model completely separate. We separate the data to each of the machines. So we have different machines with a complete copy of the model. Each machine gets a different portion of the data. Usually this is only applicable when you have something that's complete as some sort of computation that's completely independent. So when we do training, for example, since we use batches, we can give a batch to a different machine and there's almost no places where we have to merge the data together. Of course, we probably do have to find some place to merge them to merge it together, which we'll see in a second. Model parallelism, on the other hand, is where we look at the model itself and we find how we can cut it and parallelize it in the middle. So each machine gets a different part of the model. An example of this could be each machine getting a layer in the network. This can be much more efficient, especially for inference, where we don't have to do several images or several things to run on at once. But it's much harder to do because we usually have more interdependence between the different things running through the network. There's a kind of a part of data parallelism which is called hyperparameter parallelism, which of course we have different hyperparameters and we want to check which model trains best according to the hyperparameters we set. So we can just run training on different machines, giving each machine a different set of hyperparameters. So looking at data parallelism, a common one, just as an example, is called parameter averaging. We'll initialize the network parameters randomly based on the model configuration. We'll distribute a copy of the current parameters to each worker, then train each worker on a subset of the data, and set the global parameters to the average of the parameters from each worker. So this type of a thing could be done with, for example, training in batches. We'll take several machines. In this case, we have 4 machines over here. Each machine will get a batch of data, a batch of the inputs. Each one will run its training on it. And then at the end, we'll stick in the loss from each type of thing like that, bring the average, and then back propagate it through the model. Model parallelism, as I said, is a bit harder, but convolutions are a problem that can have some model parallelism. So model parallel convolution can be done, for example, by output region. So here we can take the output maps, for example, and divide them into parallel regions. We have to have some sort of halo that overlaps between them, but we can parallelize this pretty well. Another way of doing it is output maps, not output regions. So each output map can be done by a separate machine, can be learned by a separate machine. Fully connected layers are much more straightforward to run parallel. We can actually do this matrix multiplication in a completely parallel way because there's no weight reuse between the different parameters in these connected models. So if we have 16 million multiplies in a fully connected layer, they're actually independent from each other, and we could divide it into 16 million independent and parallel computations. Or probably we won't have 16 million machines, but we can do it to any number that's underneath that. So that was a very, very short overview of parallelism. And the thing is that now we're going to want to use parallelism in training and in inference, but especially in training. And for that, we're going to see what kind of hardware can be used. And we'll start with traditional programmable hardware. So if we look at a spectrum of architectures for deep learning, we start with the traditional hardware that we've always had, or always in the last several decades we've had in our machines. So of course we have the CPUs over here, but there's also GPUs which have become popular for deep learning in the last decade or so, but we've had them around for a while. And then different options that are kind of newer. So what we call a soft DPU, which would be like an FPGA, accelerator, or some ASICs that are especially made for these things. And there are all these in-memory compute types of options, which I will only really briefly discuss. I'm not going over them deep inside this lecture series. So let's start with the CPUs. So can CPUs be used for deep learning? And actually that's the way it used to be done, and that's the way it was started because we all use CPUs. So CPUs, however, they're generally optimized for single-threaded performance. So they're not made for this type of an embarrassingly parallel problem. If we take Intel's desktops, we have these Core i3 to i9s. They usually nowadays have something like 2 to 10 cores. Okay, if we take the high-end Intel or AMD CPUs, they can have up to 32 cores. Usually there'll be 2 threads per core, so they can be up to 64 threads. And there are servers such as the Intel Xeons or the AMD EPYCs. They'll have up to 64 cores or 128 threads. And you can see here the speed up of going from 1 core to 6 cores when we're doing a number of frames per second, and we see that it does give a substantial speed up if we're going to parallelize this type of a task. But again, this is a small number of cores relatively. Intel put out a series called Intel Xeon Scalable processors. Those have more cores. So the 28 cores are 56 threads per sockets, and you can put up to 8 sockets, which gives you quite a few CPUs to run on. And it also has a big DRAM, so there's up to 1.5 terabytes of DDR4. And if you take the price of a Xeon Platinum 8180, that's about $10K. And another thing is they put out these AVX 512 instructions. So Intel for a long time already has had these vector extensions, these instructions that can work on several words at once. So their latest one is called the AVX 512, and there's 512 bits in an instruction. And out of them, they have these special instructions called vector neural network instructions. So the AVX 512 VNNI, which are specifically all kinds of fused max and so forth for doing deep learning. They also have support for the brain floating point format, the BF16, and when you take these two things together, they call it the DL boost approach. So this is inherent support for machine learning type data flows inside the Intel architecture. Intel also made an attempt for a heavily multi-core processor, but again, we're discussing a typical CPU type. They just decided to put lots of cores, and this was a project called Xeon Phi. So the Xeon Phi 7290F is 72 cores, 4 threads per core, which equals 288 threads that you can run in parallel. And its peak performance is 3,500 gigaflops for double precision FP64 operations. It requires 260 watts of power and costs about $3,500, and you can see a picture of it over here. The next generation of Xeon Phi was called Knight's Hill. If you look in different deep learning courses about hardware from the last few years, they'll be discussing it a bit. It was delayed due to problems with the 10 nanometer processes you probably heard about that Intel has been having over the past few years, and eventually they canceled the Knight's Hill project in November 2017. That probably has to do with Intel going and buying a number of companies that deal with specific hardware for deep learning. Some of them we'll discuss later, but these include Nirvana, Movidius, and Habana Labs. When we discuss CPUs, we usually discuss interconnect called PCI Express. So that's the fast interface that's usually used with CPUs. It's used to connect CPUs to different peripherals at high speeds, or specifically to GPUs. Okay, so usually you have the CPU as a host that does the control, and will use a GPU for acceleration, such as graphic acceleration traditionally, and it will use a PCI Express connection. It needs to support as many lanes as possible to communicate with many GPUs, as we can see over here in the illustrations below. And Xeons usually have 64 PCI Express version 3 lanes. As you can see, PCI Express version 3 supports 985 megabytes per second per one lane. So if we take 16 links, we get 15.75 gigabytes per second. And if we go up to the next version, which is PCIe version 4, it doubles that to 31.51 gigabytes per second for 16 lanes. And the expected PCI Express version 5 gets double that again to up to 63 gigabytes per second for 16 lanes. So that's a high-speed interconnect, but we'll see that it's not actually that good for deep learning, and it's not enough. So that brings us to the GPUs, which are more popular for deep learning. So just let's go over what the difference between a CPU and a GPU architecture to get a high-level understanding of this. So a CPU, as we've been discussing, it has a few cores. In fact, it's only had a few cores for the last 15 years or so, 10, 15 years. But again, it doesn't have many cores. It has several cores. It has lots of cache, which is in a very large hierarchy where we bring from the DRAM, we bring the data in several levels, bringing it closer to the CPU itself. It has a handful of threads, and it can run independent. It's good for running independent processes. The GPU, on the other hand, is very different. Here we have hundreds of cores. Okay, so as you can see, they're these big cores. They're these SIMD, single instruction multiple data machines. They support thousands of threads, and their single process execution it's not as fast as the CPUs, but it can do these single processes just on many cores in parallel to take care of small problems, but many of them at once. And in the case of deep learning, GPUs really are much more adapted for that. So when we talk about GPUs and using them for deep learning, we usually describe it as a GPGPU, or a general purpose GPU. So a GPU is made for graphics, but when we go and use them for different types of problems, such as linear algebra, or specifically for deep learning problems, then we call them often a general purpose GPU. So I want to understand what types of GPUs are out there and which ones are used for deep learning, and this is really confusing. I mean, it's actually really confusing. So again, GPUs were originally only for graphics and gaming, and there are three major players in this field. So NVidia, they have this line called GeForce, which is for consumers, and they have their Quadro cards that are for workstations. AMD, which used to be ATI, were the big competition of NVIDIA in the GPU market. Their line is called Radeon, and that's for consumers, and Radeon Pros for workstations. And then you have Intel, which several years ago started integrating Intel HD graphics onto the CPUs, and soon we'll have this Intel Xe standalone that they've been promising. So those are the three major players which are making these, that have been making these GPUs for the last long time. Then people started using these NVIDIA cards for deep learning, and actually NVIDIA exploited this and it really took off, and they made a lot of software and a lot of stuff specifically to enable deep learning on it. And they introduced something called the Tesla series for training. So they started making specific high-end GPUs that are supposed to be in data centers and used for deep learning. AMD has followed recently with the Radeon Instinct, but they're really late in the game, and they're way behind NVIDIA in this field, and they're not as popular. Lately, NVIDIA has put out the Tegra SoC series, which has been marketed for edge inference. So not only for training, but also for the edge. So if NVIDIA is the leader in this, I'm going to go and discuss NVIDIA kind of exclusively. And it gets really confusing because their microarchitectures have strange names. So let's start with this. They have the series, which we discussed before. So there's the GeForce, which we said is for consumers, the Quadro for workstations, and the Tesla is specifically workstations for deep learning training. But in addition to that, they put a name on their product, which is the generation of the microarchitecture, and this is named after famous scientists, a few of whom we see here on the side. So Tesla, Fermi, Kepler, and Maxwell, those were the older versions. And recently, especially since they've gotten into the deep learning space, that we've had Pascal, Volta, Turing, and Ampere. Okay, but there's a problem here because we have Tesla over here and Tesla over here. Tesla is both a series and a microarchitecture, and that gets really confusing. So if we take a card such as the Tesla P100, well, P stands for Pascal, so it is in the Pascal architecture, but since it's a Tesla P100, it's a Tesla card for deep learning. Okay, it has a GP100 chip, and P again is for Pascal. The Tesla V100 on the same type of style, the V is for Volta, okay, and we have a GV100 chip, but we call it Tesla because it's a Tesla series for deep learning. Actually, this has really confused people, and last week NVIDIA came out with their new Ampere chips, the A100, and they don't call it Tesla anymore, probably to remove this complication. Okay, it gets even more confusing when you try to figure out which is the best card. So the recent Quadro RTX and Titan RTX, which both run under the Turing architecture, are really good, but they're not marketed for deep learning training. So how do you actually pick which is the best card? And we can just see there's this graph by Intento, which shows all of the NVIDIA GPUs and other things as well, such as Intel and so forth, upon a graph where this one, there's many versions on their website with the number of gigaflops of FP32 they can do. And you can see it's a widespread, and you have to choose your card according to what type of applications you plan to run, how much money you want to spend on it, and so forth. So it gets really confusing here. There are a lot of blogs that explain about it and so forth. But I hope I gave you a few words about what the names mean and so forth. So GPUs in a nutshell. Again, as I mentioned, GPUs perform what we call SIMD, or single instruction multiple data operations. And we can see kind of this processing flow on CUDA, where we have over here, and this is a little figure here from Wikipedia. What we do is we copy the processing data over from main memory into the GPU memory. Then over here we have the CPU, which is the host, or at least the host on the GPU itself, send out a list of instructions to run. So it instructs what the processing should be on this data that we copied over. Then we have all these cores that are in parallel to each other. They all apply the same instructions onto the memory that we copied over, onto the data that we copied over from the memory. And finally, we copy the result back into the main memory. So that's the type of a thing that a GPU would do. That's a single instruction multiple data type of processing. When NVIDIA talks about it, their nomenclature says that they have something that they call streaming multiprocessors, or SMs. And these streaming multiprocessors, they have many CUDA cores. CUDA stands for Compute Unified Device Architecture cores. So here we can see the Fermi architecture, and it has 16. So there's 8 over here and 8 over here of these streaming multiprocessors. So each of these green kind of areas is an SM. And this is what an SM looks inside. And you have, as you can see, these CUDA cores. Okay, many of these CUDA cores, but you also have these other types of units, a load store unit and so forth, and you'll see in the different versions they change actually what's inside these streaming multiprocessors. You also have some shared memory and some interconnect register files and so forth that are along this thing. Inside the CUDA cores, you can see you have this dispatch port, the operand collector, a floating point unit, an int unit, and a result. So they're kind of simple CPUs that are running in simple cores that are running inside here, but many of them in parallel that are getting this list of instructions and using some common memory together. So why does this work? Well, look at it. If we take speed up and efficiency, you can see that a Titan X, which is a Maxwell architecture, versus a Xeon, an Intel server, and you can see that the number of frames per second we get for no batch of AlexNet, we get a 5.3x speed up for this Maxwell GPU, and when we actually batch the data and we can do things with a lot of more data parallel, we get this even much larger type of a speed up over here. Okay, and same thing if we go to inference and we take the Tegra SoC, which I told you the Tegra is their line of SoCs that they're now selling for deep learning. It doesn't have that much of a better speed up if you're looking at just the number of frames per second, but it is much more energy efficient than a Core i7 at doing inference. So looking down more at the architectures that NVIDIA has recently, rather recently, they put out something new pretty much every year, so have put out for deep learning. So Volta was a big step when they took forward. So here's a Volta GV100 chip, which has 84 streaming processing units. So you can see here all these stream processing units. And if we go and we look at a quarter of one, so just one of these green things out of this 4 green things in a streaming processing unit, and we open it up, we see that inside now, different than what we saw before in the Fermi, I think, architecture we had. Here we have all of these floating point 64 units, all of these integer units, all of these floating point 32 units, and then we have these 2 big matrices that are called tensor cores. So we want to know what a tensor core is, which was this new beast that came out, and you have some little illustration of how they went from the Pascal architecture running deep learning to the Volta tensor cores. And what it is this unit that can do 4x4x4 max in a single operation. So it's this fused multiply accumulate unit that can take these these matrices of 4x4 size, do 4x4 plus the previous result, and actually does it in mixed precision. So it can take FP16 inputs and do the accumulation in FP32 to really get this really nice. And you see kind of an illustration of how it does here. Two FP16 operands, they're multiplied and they're accumulated together with their previous result, which is at FP32, putting out an FP32 result. So these are these tensor cores, which are really, really made for making matrix multiplication faster. The Turing architecture, which was until a few days ago the most recent architecture by NVidia, it actually introduced support for int8 and int4 precision. So this was a big thing that Tesla put out in their that NVIDIA put out in their Tesla T4 cards. They didn't actually put out their really high-end cards for deep learning in the Turing architecture. They had their graphics cards, their more gamer-oriented graphics cards had their higher performance, but they did have this support for these int8 and these int4 types of operations, which actually get really nice speed up for when we start doing reduced precision. And this is hot off the press, and this is what just came out a few days ago. So the Ampere architecture, we knew the name of the Ampere architecture, but the first release was put out in the big keynote that the CEO of NVIDIA gave a few days ago. And this is a real beast. This is a huge improvement, and we can say that almost every time NVIDIA comes out with one of their big events. But the GA100, that's the chip that they have here, and here you can see a picture of the whole chip. Here you can see a picture again of the streaming multiprocessor. And here's a nice picture that they put out of their whole card. So here we have up to 128 streaming multiprocessors and 8,000 CUDA cores on the chip. It has 54 billion transistors on the chip in a 7-nanometer processor, and its size is 826 millimeters square, which is just about as big a chip as you can get on a reticle. It has 6 stacks of HBM2, which has a bus of 5,120 bits wide. The interesting thing is that should be 48 gigabytes of DRAM, but they only actually show that they have 40 gigabytes of DRAM. It could be that one of the chips of one of the stacks of HBM2 is for redundancy. It could be that they're only delivering it with 5 chips and not 6, 5 stacks and not 6. The boosted clock is 1.5 gigahertz almost, 400 watts of power. Okay, they introduced a new format called TF for TensorFlow 32. Okay, so or tensor format 32, and that's 19 bits. So instead of the brain floating format of 16 bits, they add another 3 bits, and therefore they can get the precision of FP16, but with the exponent of FP32. So that's NVIDIA's new format they just are announcing with this. It can do 312 teraflops for these TF32 calculations, which is 20x faster than the last big Tesla card that they had, the V100, but the V100 was measured at FP32, which is a different format, but still that's what you can get. And if you look at the FP64, they provide 19.5 teraflops, which is 2.5x faster than the V100 at FP64. Again, sometimes it's not exactly apples to apples, these types of comparisons, but it really is a beast, this Ampere. Here's a big table of comparison of the Pascal architecture, the Volta architecture, and the new A100 Ampere architecture. And you can see the different things and the different options it can do. Of course, it was a 16 nanometer going down to a 12 and to a 7 nanometer. The die size got quite a bit bigger, and the number of transistors really it was 2.5x over what we had in the Volta. Okay, more power. A huge cache. So here you see that there's 40 megabytes of cache, right? And really faster DDR, more memory. Everything got much bigger here for the Ampere. So this is going to make a real difference in the data center. NVIDIA, if we saw before that CPUs use PCI Express to do their communication, well, NVIDIA has their own proprietary type of a link called NVLink. And NVLink is an energy efficient high bandwidth path between the GPU and the CPU, or between different GPUs. NVLink 1.0 was 80 gigabytes per second, 2.0 150, and now with the Ampere architecture they also announced the new NVLink, which is 600 gigabytes per second. There's also something called Infinity Fabric, which is a similar technology by AMD, but again, since really NVIDIA is the leader in this field, I've been showing you the NVIDIA types of cards and their names. So NVLink is really what NVIDIA is providing to do these really fast connections. When we say NVLink, we can connect several of these cards together in some sort of a crossbar fashion and keep really high bandwidth between them. But you can also get this thing called NVSwitch, which is a fully connected NVLink, and already announced that I think the Department of Defense is using a 6 NVSwitch type of configuration, which provides 4.8 terabytes per second of bandwidth. So that's really, really a lot, and that's this type of configuration that we see over here. One of the things about NVLink is called unified memory, and this is a quote from NVIDIA, that one of the most dramatic programming model improvements in the history of the CUDA platform is this unified memory, and it's a pool of managed memory shared between the CPU and the GPU. It's not yet supported by a lot of deep learning frameworks, but it means that in the past, a developer would have to have the system memory and the GPU memory, and they'd have a separate memory space, and the programmer would have to deal with that. Now with unified memory, it's just all one pool, and you can program it and not know the difference between the CPU and the GPU memory and just use it all, and that really helps and makes life easier for the programmer. So that was GPUs, but there's another player in the general purpose market, and that's the FPGA, so let's not forget them. So Xilinx is a big player also in the artificial intelligence field, and they have their line is called the Xilinx Versal AI Core. They brand it an ACAP, Adaptive Compute Acceleration Platform. Their big product is 7 nanometer FinFET, 37 billion transistors, 885 megabytes of SRAM, 400 AI engine cores. It includes DSP and AI compute engines, network on chip and memory, both DDR and HBM. You can connect it to high-speed interfaces, Gen 4 PCI Express, Gen 5 CCIX, 600 gigabit Ethernet, SerDes and RF. You can see a picture of it over here on the right. So basically what Xilinx is saying, listen, we were giving you this massive chip that can do all these things. You program into it whatever type of accelerator you want. And they call this, you could call this a soft DPU or something like that. One of the big players that is using this type of a soft DPU is the Microsoft project Brainwave. So Microsoft came out a few years ago and they said, we're going to have a deep learning platform for real-time AI inference in the cloud and on the edge, and it's going to be based on soft neural processing units. So what that means is that they have now in the Azure cloud many of these FPGAs. You can rent an FPGA, you can program onto the FPGA whatever your accelerator is, and so it augments CPUs with an interconnected and configurable compute layer composed of programmable silicon. They provide 2 layers of this. One is in the Azure cloud, so it's called Azure Machine Learning, and you can distribute models onto Intel Aria 10 boards. Intel Aria are the what used to be Altera, bought by Intel. They're the big competitors of Xilinx in this. So Microsoft is working with Intel on that. And at the edge, they're giving something called the Azure Stack Edge, where Microsoft ships you a cloud-managed device with a built-in FPGA. So Microsoft has really bet on this, putting out FPGAs out there that you can rent and you can reprogram them and so forth. You obviously lose a lot in the fact that you don't have this hardwired ASIC or this really tightly developed GPU for running the deep learning stuff, but you can really optimize it for your application by reprogramming your FPGA. So that was our overview of traditional programmable hardware. And in the next part of this lecture, we're going to go into the recent specialized platforms for deep learning. So the alternatives to buying a CPU, GPU, or FPGA.